Alright. So thank you guys for coming. So this is the third online meeting, 2016 for MPH 218. So in this one, I want to finish looking at the stuff from chapter 1. So the subject has 3 parts to it, as you may have noticed. So the first part is looking at curved surfaces and extending differentiation. And so that's what I'll focus on today, is that partial differentiation aspect. So looking at all different ways that we can do partial differentiation. So I want to try to show you where some of it's useful for. So, I mean, apart from being able to do stuff, just try to show you the bigger context. That's something I would like to try to do today. I'll see how we go. The other thing is, some people have asked some questions at various points in time, looking back a bit. So I'll do those towards the end, is my basic plan. So if you have any questions you want to cover at any point in time, please throw away. So again, I prefer to head in your direction, etc. So looking at partial differentiation is a really good way. It pretty much is the differentiation you do when you've got more than one variable. So there's different aspects to it. So I'm going to do them in a few. Just it's a fire alarm. I hope that doesn't stuff me up. Oh, there you go. So first one to look at is the idea of a gradient vector. So I really am assuming you remember to do partial derivatives. I'll do some practice as we go through, but you need to practice, revise it in your own self. So first idea is the idea of a gradient vector. So for a given function of many variables, the gradient vector is just a vector considering all the different partial derivatives. So if you've got a function of 2 variables, it'd be a vector of 2 components. One is the first derivative, second one's the second partial derivative. That's the idea. So gradient vectors are useful in many things. They are a nice, useful way of writing compact notation for many of the things we do, including tangent planes, differentials, direction derivative, which I'm going to mention here, as well as chain rule, etc. So it's a really useful way notationally, and we'll see that idea coming up in other things. So it's the first of the vector fields that we'll consider. And at the end of the day, we would like to consider how to do calculus on vectors. And so that's where we're heading towards ultimately, but so that's our first one. So gradient vector, just a vector of partial derivatives. So the partial derivatives really are looking at the slope of a surface or some other object for different particular cross sections. So they're really just looking at slopes in different cross sections. So what we normally want to do is, well, if you're actually on a physical hill, then what really matters is not the cross sections and slope of cross section in 2 different directions, but really what's the slope of the hill I'm walking up right now, or what's the slope in a certain direction. So a much more useful thing is to get the slope in a given direction. That's called a directional derivative. And the formula I use for that is d for directional derivative, a subscript of the direction I'm going in and of the function. And if I want to know what the values are, I would put open brackets and the value, the x, y values, etc. I'm trying to sub into. So to work out this directional derivative, basically it ends up being a dot product between this gradient vector. So that's the gradient vector there, dot product with the direction you're going in. Now, just a few tips here. This is a really important one. Is most people know that formula. The formula only works correctly is if this directional vector here is a unit vector, i.e., it has to have had length 1, and that's the most common mistake people will do with this sort of directional derivative. That's why I'm mentioning it. And so, if you're given a direction, you need to make sure you divide through by its length first in order to make it length 1. Now, to give a sense of what this directional derivative is, I want to tease this out as the next example, is the directional derivative is, so the gradient vector really is the direction of steepest descent. So it's the steepest direction going uphill. That's the direction. And the magnitude of this gradient vector is that slope in that direction. So it's it gives you the maximum slope. That's a really good way of trying to understand it. So I'll show that in pictures in a second, in an example. So Here's let's do an example. If you can't read it, let me know. Remember, if you need to, if you go on the main screen on a PC, this is, if you click the little, on the top right, there's an icon which makes the screen bigger. So I've got a full screen. It might make it easier to see if that's necessary. And again, on an iPad or a phone, etc. Phone, you're doing well. But if you're on a tablet sort of device, you can tap on it, I think, to make it bigger. Anyway, so here's an example. I've got a surface here. Its z is equal to various things here. You notice the highest term is the squared term, so it happens to be a quadric surface. So we could try to understand that way. I've done that just to make it simple, but the process works for higher order stuff too. And I want to consider a certain point on the surface. A question I have in mind, sort of the bigger problem I have in mind, is given any function at all, can be quite complicated. Given a starting point, how can I then, from that starting point, end up working out what a nearby maximum value is? That's sort of a key sort of problem I would like to have considered in my back of my mind to show an application in this one. So I want to show you in this case. So a key idea is working out the gradient vector. That's really what happens, useful in that sort of circumstance. So I've got z is function of x's and y here. So it's a function of just the two variables. So the gradient vector so the gradient vector here is a vector, because it's two variables, you have two components. Just two components. The first component, and each component would be the different partial derivative. So the first component would be the first partial derivative. Now, I write that down different ways. For short, z is the function, and the subscript x is the partial derivative with respect to x. Alternatively, I might write this as partial z, partial x. So two different ways of writing the same thing. The second term here would be the partial derivative of z with respect to y. So they're two different components. And it's just a matter of working it out. So maybe you guys can tell me, because this one's pretty simple to type in, what is the first partial derivative? What's the partial derivative of z with respect to x of this particular function here? Someone type it in. So the function, if you can't read it, is z is equal to 2x minus x squared minus 2y minus y squared. So what is the first partial derivative? And someone's got it as 2 minus 2x. So when doing partial derivatives, remember the trick really is any other variable just think as being constant and then just do differentiation normally. That's really what the trick is. So the y's here are constant and you get nothing. So the partial derivative of z with respect to y is what? It's the other one to do. So minus 2 minus 2y. So again, you just need to do some practice with it. And again, signs are always the easiest places to make mistakes. So that's the gradient vector. So that's two components. I can write it down using tuple notation like I've got here. You can also write it down using the IJ notation. Just spotting a mistake I've done here. And that's, I can write it as, say, 2 minus 2x I plus minus 2 minus 2y j. They are the same thing, and so just pick whatever you find more convenient. I often find the first one easier to use, so that's what I'm going to do. What's going to be useful to us is working out what the value of this gradient vector is at our point, which is what the question asks for. So it's find the gradient vector at P. So we actually haven't answered the question yet. So the gradient vector at 3, 1. And what you need to do there really is just sub the numbers in. So sub in x equals 3, y equals 1 to get an answer. Sub in x equals 3, you get minus 4. Sub in 1, you get minus 4. So that's what the gradient vector is at P. So that's the first bit. Now we have the gradient vector at the point we can do stuff with it. So it says, let's find the slope in the direction of a given vector. So this is a vector. The first component is 1 root 2. Next one is minus 1 and root 2. And so we need to find the direction. So at first glance, you think, well, the directional derivative in that direction of z would be the gradient vector at our point. Question. Sorry. So the directional derivative at our so the slope from our point in the direction of u normally would just be the gradient vector at our point dot product with the direction, dot product with u. That's what would normally be. And let's do it in this case, and then we'll say why we have to be a little bit more careful on what I'm being at the moment. So the gradient vector is minus 4, minus 4. We're taking dot product. U, the first component is 1 on root 2. The second component is minus 1 on root 2. It's a minus sign there. So I'm going to take the dot product. Can someone tell me what the answer is? So if you take the dot product of those two vectors, what do you get? Again, if you get any questions, fire them away. That's not a problem. I can see someone trying to answer, then it's not coming up properly. That's fine. So if you look at it, you may not be able to read my writing very well. So the dot product would be just take the multiple of each corresponding term. The first one is minus 4 times by 1 on root 2 plus the second one. So you get minus 4 times by minus 1 on root 2. So minus 4 times by minus 1 gives you positive 4 on root 2. So you get double negatives and make it positive. So you get minus 4 on root 2 plus 4 on root 2 gives you 0. So again, got to be careful with signs. That's okay. So you get the answer of 0. What does that mean? I mean, the question here says interpret the result. So basically, we've got to pick the direction, and we found that the slope in that direction happens to be 0. What does that mean? Well, it means that if you're walking along the surface, in that particular direction, you're not going uphill or downhill, you're staying at the same height. So you're not changing your height in that direction. That's what the 0 means. So just showing you some pictures of what's happened here. So this here is the contour map, this thing. So that's a contour map. Blue is the direction we've just gone in. So that's the blue one we just considered. So you can see that the red line's the contour at 3, 1. We're just walking along in the direction along the contour. So we're not going uphill or downhill or just along the surface. You've got the 3D picture, which sometimes is harder to see. Again, looking at the blue arrow here. So we're at a point on this particular surface, so you can see it's an elliptic paraboloid. We're actually walking along, not uphill or downhill, just along the edge of the surface. So keeping it the same height. Now, if you keep walking in that direction, it wouldn't be true anymore, but just for a short distance, you're staying at the same height. That's sort of a sense of the directional derivative being 0 there. So what we want to do then is, well, so done the first two. Let's look next one. Let's find the slope in a different direction here. And you might be tempted to do the same sort of thing. So I just replace the components of so they're exactly the same sort of stuff. I'll change the color to see what I'm doing different. So you might be tempted to just go, well, the next vector I've got here is got a component of minus 3 and minus 4, and do the dot product before and get the new answer. But that would give you the wrong answer. So you have to be a little bit more careful than I was the first time around. And let's explain why. So I deliberately made a mistake just to emphasize it so you don't make the mistake yourself. This formula only works if this vector u here has length 1. It has to have length 1 for it to work. The first one did. So if you work at the length of this vector, it's 1. So let's work out, call this little u. The length of u, which I'll just put an absolute value sign. And it's easy to do the length squared. So the length squared is just the first component, so minus 3 squared, plus the second component squared. And if you got more components, so just summing just the square of every single component, so you're getting 3 squared plus 4 squared essentially gives you 25, and so therefore taking the square root, the length of u is 5. So the length, if you did it in the first case, the length would be 1, but in this case the length is not 1. And since the length's not 1, we have to just do one more extra step. So before we can consider stuff, we really need to normalize it. So what we need to do is we need to consider the normalized form, and I just put a little hat over the top, is how I write it down. So putting the hat just says I'm normalizing it. And all I need to do for that is to get my first vector and just divide through by its length. That's all I need to do. So I had -3, -4 before. So what I'm going to do is divide both of them by 5. Just to make it into length 1. So, and again, you can try length now. So -3 and 5 squared plus -4 and 5 all squared. Add them up, you get 1, which is good. And that's what you needed it to be. So what I need to do in this case is, in order to get the right directional derivative, I need to change this to be on 5 for it to work. And when I do that, as long as I can do the rest of my calculation correctly, I'll get the right answer. So if you do this product, you get -4 times -3 and 5 gives you positive 12 on 5. -4 times -4 gives you 16 on 5. Minus gives you 16. Add those up, so 12 plus 16, or divided by 5 gives you 28, 50, 6 on 10, so 5.6. So the slope in that direction, if I have a mistake that is 5.6, which suggests it's pretty steep, right? So a slope of 1 means that's a 45-degree angle you're going up. So slope of 5.6 means it's actually really steep in that direction. So you really are going, you're going quite steep uphill. And so unless you're a good climber, I wouldn't be taking that route if I were you. So you certainly wouldn't be driving a car up at that sort of slope. So that's just trying to use directional derivatives. Last two here are just some definitions. Find the direction of the steepest descent. So the direction of the steepest descent happens to be just the gradient vector. So this is just knowing it. So, and again, this is the really important use for it, which is why I mentioned it. And so that happens to be -4, -4. That's the direction. And you can see it's pretty close to the -3, -4. So the one we consider it's going to be close to it. That's that one done. Find the slope in that direction. So again, just a definition. So the slope in the direction of the steepest descent is the magnitude of this vector. So it would be just summing of the squares, so -4 squared plus -4 squared. So finding that length thing again, and then square rooting it. And if you do that, -4 squared, 16 plus 16 is 32. So you're getting root 32 is the slope in that particular direction, which gives you, I don't know, maybe 5.8-ish, something along those lines, approximately. I'm guessing more than anything else, though, to tell you the truth. So you can see that this direction we picked before is pretty steep, but not quite as steep as the steepest direction. So again, just showing you visually what's happening here. The black arrow is the gradient vector, direction of the gradient vector. So that's the steepest direction of steepest descent. The green one is the other one we consider as the -3, -4. So you can see that those, like the black arrow, let's take the black arrow, you can see it's actually going in a direction that's in the steepest direction. So it's heading right uphill. So it's heading directly up the contours. And you can see the top of the peak really here is bang here at 1, -1. So you can see it's heading right towards the top of the peak here. And that's why it's so steep and heading upwards. Or if you want to see the 3D picture, you can see the black curve is heading directly uphill. So this leads to a way of, if you've got a complicated function, so long as it's smooth, then one way of trying to work out a maximum is make a guess. So in this case, we guessed 3, 1 as our possible place for maximum. Then what you can do is you can work out the gradient vector. The gradient vector tells you the direction that of steepest descent. So if you just go in that direction a little bit, so just hit I, just walk uphill a little bit effectively, then that will get you closer to the maximum is the idea. And it'll get you the close maximum quicker is what it seems to be. And then once you're uphill a little bit more, you work at the gradient vector again, and work out the new direction, which hopefully is similar, and keep going. So every so often, take a few steps, we work out your gradient vector, and keep going. And eventually you'll zigzag up, and eventually you hit towards the peak. And after a while, you can't go up any higher, and you've worked out what the maximum is, or let's be honest, a local maximum. You can get many peaks sometimes. So this idea of that's called the algorithm of steepest descent. And really the heart of that is finding the gradient vector. It's not sophisticated. You can make it slightly more sophisticated by using other partial derivatives as well. But that's covered in a greater detail, for example, in the subject MTH 307. So 307 is numerical, it's called mathematical modeling, but part of that, the end of that subject is looking at how to find maximums for different funny surfaces, etc. So looking at generalizations of that sort of idea. But you can see the gradient vector really is important for that sort of stuff. So just trying to show you the bigger picture. And you might go, gradient vector, it's easy to work out. What do you ever do that for? Well, just trying to show you what it's useful for. Next thing I want to mention is the idea of the chain rule. So you know the chain rule for one variable. Basically it allows you to take the derivative of a function. And it's the same thing here. We want to take the derivative of a function, or more generally, a partial derivative of a function. But in this case, how do you work out when functions have more than one variable? And the case is to work out the way to work out the derivative of z when z is functions of x and y. When you're trying to work out with respect to some other third variable, what you end up doing is you have to do some sort of term for every single variable you have present. So if I've got to x and y only, then you have a term for each of them. And then for each of them, you just do the partial derivative of z with respect to that one variable times by the partial derivative of that variable with respect to the one you're trying to do at the bottom. So you have this sort of basic pattern all the time. That's really what the chain rule is. So as I said, it's a way of working out the derivative of a function of a function. It just happens to be you've got functions of many variables. That's the only difference. So you can do lots of trivial examples where I just define, functions of functions, etc., and you can apply them in. I was just trying to think of an example which is a bit more useful to do, perhaps. So here's one here. So if you've got again, got any questions, far away. So if you've got a pendulum, so pendulum is you've got a string. This happens to be, if you've got a string about 10 meters long, this particular one here. So if the angle between the string and the vertical is theta, and the angular velocity, so the angular velocity, which normally write as omega, is a w, then you can work out that the rate of change of this angular velocity, so i.e. the angular acceleration, is minus sine theta in general, and the d theta dt is the angular velocity. So these are the formulas. So if theta is really small, minus sine theta is pretty close to minus theta, and you get the small angle approximation to a pendulum, which you probably have seen elsewhere. And the formula is well known for it. You get simple harmonic motion. You may have seen it at school even, I'm not sure. But I've written down the more complicated version where you've got a minus sine theta instead. So this is the not small angle approximation. And the formula becomes a bit harder to solve that way. And so trying to solve this couple differential equations is difficult. So let's not try to do it. But nevertheless, we still want to consider different functions that might be functions of both angular velocity and theta. So I've got one here. So I've got a function of two variables. So the function is of w and theta. So what I want to work out is what's the derivative of this function I've made up with respect to time. So here I've got f is a function and a w and theta in themselves are functions of time. The issue is I don't really know what they are explicitly, but I do know, fortunately, how they both change with respect to time. And so what I can do here is when trying to work out the derivative of a function, I can use this chain rule. That's what as always. So pretty much for each term you consider. So the two terms are w and theta. So the first term is w. So I just do split up the df dt as two parts. So del f del t. So two parts. And I want to do that for every single term. Another del f del t over here too. And then what I want to do is just put the individual variables in. So the first variable I've got is omega. And the second variable I've got is theta. And what I'm running down really is just the chain rule. And I've deliberately picked different variables that make sense in this context, but just showing that they're just letters. That's all they really are. So what I have to do, and again, I want you to try to tell me some of these things, if you can. First, you have to work out what the part derivative of this function f is with respect to omega. So what is del f del w del omega? Can someone type it in? It's more important for you to practice. So you're getting omega. Yeah, it sounds good. So just w. What is del omega del t? Well, that's all right. Don't have to work at anything at all. I already have the answer. The answer is up here, and it's minus sine theta. So that's the first term. So minus omega sine theta, effectively. Next we have to do is del f del theta. So we have to work at the partial derivative of this f term here with respect to theta. Again, can someone tell me what the answer is? Anyone? I know there's a lag. That's one of the downsides with this technology. That's okay. So del f del theta is, well, omega here is constant. Basically, when you're taking partial derivative with respect to theta, we're assuming all the other variables are constant. So omega, we're considering just be constant. So derivative of that one would give you 0, so nothing from that one. Then you got minus cos theta. The partial derivative of that one with respect to theta would be, well, derivative of cos theta normally is minus sine. And so you got double negative, so if you minus minus gives you positive sine. Which is what someone wrote down, thank you. So that would be the del f del theta. Del theta dt, again, we just copy down, that's just omega here. So times by omega. So if you try to simplify that expression, what do you end up getting? Can someone tell me, what do you get when you simplify that down? Again, it depends how well you can read my handwriting. Hope it's all right today. Just waiting for people to respond. Yeah, and you get 0, that's right. So when you do all this, you're getting 0. So although f at first glance, where did you ever get that from? When you take the partial derivative with respect to time, you end up getting 0. What does that mean? Well, df dt is a straight derivative. So it's just f is some expression that I've worked out. And I've worked out that with respect to time, it gives you 0 derivative. What does a 0 derivative mean? 0 derivative means it's a stationary point. But this is true for all values. So this isn't stationary for one single value. This is always stationary. So if it's always stationary, that tells me that f here is a constant. That's the great thing. So that's the key thing. So this expression here, so half the angular velocity minus cos theta, is a constant for the this pendulum. So you can do various things. So cos theta here is between -1 and 1, for example, at the grand scheme of things. That's equal to a constant. That gives you some limitations for what the maximum value for omega can be and what's the highest angular velocities, etc. And that's what that tells you. If you can work out what the constant is, so just by subbing initial conditions in, that gives you a good idea of the relationship between omega and theta and general terms are, etc. It's a bit of an annoying curve to try to draw. You could do it. You can try to sketch. You can make omega the subject, for example, and draw the relationship between the two and see the phase portrait for the pendulum. So this expression is really helpful to understand what the pendulum is. Now, where I got it from was by integrating these things middly, but just trying to show you how you might use the chain rule in various circumstances in a meaningful sense. That's what I'm trying to cover for this example. So getting examples far away. So more artificial examples like mixed terms make it harder. I would like it. I would normally make it a little harder than this if I possibly can, but I want to make it more realistic. So these sort of things are trying to be useful. Another application of the chain rule is when trying to find out the trying to work out, say, partial derivatives or straight derivatives for that matter, implicitly. So when you're trying to do implicit things. So basically, if you know a function and it's defined implicitly by some sort of equation, if you make that equation, whether it's in 2, 3, 4, whatever variables, you can put that all on one side. That's the real key thing. So a real key aspect here is if you make, you rearrange the equation to put everything on the left-hand side equals 0. That's the key thing here. And it can be, gxy 0, or you can have it, more variables if necessary. So nevertheless, always make it equal to 0. Then to work out the any derivative you want to at all, so dy dx or del z dx or whatever it might be, then really it's just taking a ratio of different partial derivatives of that function of g. You can see that both forms. And it's just a ratio of partial derivatives. And it's the perhaps opposite to what you might think it to be. So if it's del y on del x, you do the partial derivative of the bottom, not the top. So you can see that there's a, I'll just copy this so I can scribble over it. So again, to help you try to remember it if you ever needed to, you can see there's a crossover there. Now, you're allowed a formula sheet in your exam, so you can just have it written down. And it's a ratio of 2 partial derivatives with the big minus sign at the front of it. And really, it's just an application of the chain rule. Just plugging the things in and getting your answer. So, I just wanted to try to think of an example. So I want to consider this particular surface. So this is at first glance a surface involving x, y's, and z. So it's defined implicitly by an equation rather than by saying z is equal to something or other. And so I want to work out what a particular partial derivative is. And now, what surface does that look like? So I'm just showing it to you. That's why I picked it. And that's what this surface looks like. It's a torus is the technical name for it. It's the outside of a donut. Is perhaps more colloquially what you might recognize it to be. So it's a valid surface, which you can useful in its own right, but you have to really write it down implicitly to get it okay. So, but because it's a surface, it's important. You still like to know what the slope is. Knowing, do you want to work out local maximums, whatever it might be, you still need to know partial derivatives, so you can work out gradient vector, etc. So it's still important to be able to work out the slopes. And the slope really comes down to knowing the gradient vector, which means knowing all the different partial derivatives, etc. So that's what I want to try to work out. So in order to apply this implicit function theorem, and you can work out the thing directly, but I think implicit function theorem makes it easier. What I would do is to rearrange this to make it all on the left-hand side. So I've got an x squared plus y squared plus z squared, and I'm going to put a bar on my z to make it a little bit easier to read. Oops. Plus 8 all squared minus 36 x squared plus y squared equals 0. So um, most people can do this pretty well. The most common mistake, I think, really is forgetting to put everything on the right left-hand side first. So again, just want to flag that in the big way, trying to say you avoid the mistake yourself. By the implicit function theorem, the partial derivative of z respect to x is a minus sign, big minus sign. Then it's a ratio of different partial derivatives. The one on the top is the partial derivative of this expression. Let's call it g. With respect to the bottom variable, so del g del x. And the bottom here is partial derivative of this same expression with respect to the top variable. That's the implicit function theorem. So what we need to do then is just need to find these different partial derivatives. Now, this one is slightly more annoying to write down, so I won't ask you to type it in. Take you ages to type it in. So, partial respect x, here we have something all squared, so we have a function of a function, so we need to use the chain rule as we think of it, a chain rule of one variable, to try to work out the answer. So, we got a function of function, so the answer is take the derivative of the outside normally, so we 2 times the middle times 2 times the inside. So, so the derivative of x squared is 2x, and that's the idea. That's essentially written down. But then you've got to multiply it by the derivative of the inside. So then you have to do the partial derivative of what's on the inside. So y and z, they're all constant with respect to x, you can ignore them. So really just the x squared. So the partial derivative of x squared with respect to x gives you 2x. Then we have another term here, so minus 36 x squared plus y squared. Well, the y squared is constant with respect to x, so again we can ignore it. So really just got minus 36 x squared. The partial derivative with respect to that would be minus 36 times by 2 times by 2x. That would be the full term. Now I can see someone typing and then the message never comes up. So if that's deliberate, not a problem. But if you're having trouble otherwise, just letting you know, I guess. The other derivative we need to find is the partial with respect to z, which would be the same sort of thing. So again, you got a function of a function, and so you take 2 times what's on the inside. So derivative of something squared is 2 times the something in the middle. But this time you're multiplying by the derivative of what's on the inside. And we're taking partial with respect to z, not x anymore. So the x, y, and 8 are all constant with respect to z, so they'll just be partial derivative give 0. Partial derivative of z squared will give you 2z. Look at this last term, the minus 36 x squared plus y squared. Well, all of those, none of them have z's in at all. So they're all constant with respect to z. So taking those partial with respect to z will give you 0. So let's put minus 0 and make it explicit. And therefore, the final answer then, it's on the one we want, is going to be minus these terms, ratio of these two terms. So minus 2, put big brackets around all these different terms here. Minus 36 times 2 multiplied by 72. All over whatever the bottom was. Let's make it 4z. Should have plenty of them up as well. Oh well. And I've written a term expression down here. You can clean it up a bit, of course, and you probably can rearrange it to make it a bit more meaningful at various points in time. Um, so you can, as I said, you can um, do various things. So um, you could bring the minus sign in. You can factorize whatever it is, a 4x out the top and cancel stuff out. Would be more meaningful, but I'll just leave it at that. So you can work out, so from this, you can work out various slopes. So why this is important, I guess what you want to use it for is if you factorize the top and then solve it equal to 0, that shows you where x cross sections are stationary. So it shows you where the maximums are for different cross sections for in this case fixed y. So yeah, that does tell you some key information for you. And again, if you look at the bottom, it tells you where you got vertical slopes rather than so you got vertical points rather than stationary points, so to speak. So these things are handy to do to help you understand the surface. I guess is what the point of it all is. And putting all the information together will give you more stuff. So I picked this example because it's a nice, pretty surface as far as I'm concerned. Okay, so there's just some different applications. So just recapping, so we'll use the gradient vector, which is good for working out slopes in different directions. We've considered using the chain rule, which can be useful in its own right to work out some partial derivatives, but it's also good to work out derivatives when you want to work out things implicitly. The other thing that's handy to do is to work out the tangent plane. So I'll mention an example in a sec, so I'll just fill it in. So often when it comes to looking at functions, things which are linear are easy to deal with. And so linear things like straight lines, but that also includes planes and hyperplanes in general. They are much easier to deal with. And so a key trick often to dealing with difficult problems is to convert a non-linear problem into a linear one. Now you can't do it exactly, but you can do it approximately. So, and the real trick here is that for a straight curve, the tangent line is close to the original function, as long as you're not too far away. And same thing here too. You've got a function of two variables, then the tangent plane is close to the original function, so long as you're close to the point in question. And so the idea of a tangent plane gives you a linear approximation to a nonlinear problem. And you can use that to great effect at various points in time. So I want to try to explain where this is used in navigation of planes. This is why which is a vastly difficulty explaining to you. It's not how useful it is. It's very useful. The difficulty is how they in planes they make them as they try to put all factors in. So I'm grossly simplifying it. But before I do that, let's see how you work it. The formulas, how you actually work them out. So you've got a function of say two variables. Z is equal to fxy, and so z's the surface. So really, this is a function defined explicitly. That way. I have a point in mind, which would normally be given to you. Then basically the tangent plane is z minus the z value is equal to the partial derivative partial derivative at the point in question, x minus x naught plus, etc. So that formula just sub in. Incidentally, that's correct, and I suspect that's probably the most useful form. You can write this down as the gradient vector at the point in question dot product with the different variables x, y minus the reference point. So you can write it down as dot product between a gradient vector and a position vector. Now, is that helpful or not? Probably not to actually do calculations, but it shows you that this gradient vector crops up quite naturally in many different ways. And therefore, understanding this gradient vector is the heart of understanding this linear approximation, is the other way of doing it. Um, on the other hand, not all functions are defined explicitly. Sometimes you have to define them implicitly. So you have an implicitly defined function. So that'd be an equation involving x, y's, and z's, for example. Again, dump everything on the left-hand side, make it equal to 0. Then the tangent plane would be similar sort of thing, but it'd be the different partial derivatives in front of every single term. So again, if we look at this one here, you can write this down as saying that the gradient of g at a given point dot product with x, y, z minus the reference point equals 0. And if you think about what this means, so the formula we have for planes normally is the normal dot product with x minus a reference point. So that shows you that this value thing here is just the normal. So the gradient, so again, another geometric definition is the gradient vector is normal to the surface. So again, this here is a function of function of 3 variables. So I mean, although it's defined implicitly, if you're going to think of it being a 4-dimensional object, then this would be the different level surfaces. So this would be the gradient vector in that case would be perpendicular to all the different level surfaces in that context. So the gradient vector is useful in many regards. Let's just stick with the good old-fashioned form we've got here. Okay. So question I've got here is mostly I'll just describe it. That's the equation at the bottom. So as I said, this idea of using linear approximations for non-linear stuff is important in many circumstances. So the example I want to talk about is flying a plane. So how planes work is they have different sensors to work out their airspeed, their acceleration, so and how their orientation. So they've got gyroscopes to work out if they're spinning around, turning around. So all these different things help them work out their location, orientation, speed, etc. And they've got various sensors. And it's an inertial reference frame. So they basically using what they knew about their position a microsecond ago, looking at the sensors to work out what the new position is. Problem with those sort of stuff is there's errors that crop up, and so what modern planes do is every so often they would also get a GPS measurement, and the GPS measurement normally is more accurate, and they will combine it with what their current figures is and get an accurate position. Problem with GPS, because it's bouncing off a satellite, it doesn't come as nearly as quickly as the measurements you get on the plane. And so what the idea is, the plane will need to keep a record of what its current position is, keep updating it regularly, and as soon as it can get the GPS measurement, it uses that one to update the figures. And if the GPS satellite's down quite a lot, it still can get a good idea. So that's the basic idea of how planes, navigation works in a nutshell. The standard mechanism is to use 22 different variables to work out the state of a plane, which includes lots of things, which includes the magnetic variability in a plane of the Earth at various point in time. So they have lots of different stuff. But so let's just focus on one aspect, and that is the x coordinate of the velocity, so your speed, and your orientation. So this is orientation in the xy field. So those are two things. So that's u and theta are sort of two different variables we're to consider. Then, given you know what your speed and angle is at a given point in time, you can then predict what your speed will be in the next instance. Well, your velocity is going to be what it was before, pretty much, plus anything affected by acceleration. So part of the issue is why these things are complicated is you can get a random bit of wind gust which bumps you slightly. So you might have some acceleration in a given direction. So A is some sort of random acceleration. to make this concrete, I'll explain how it works in general. Let's make it give it a number. So 0.1. So this is sort of relationship v. So your next predicted velocity is equal to previous velocity plus 0.1 times by cos of the previous angle. So this is an update equation. And you can use this equation directly to work, knowing what your previous values are, help you work at the next one. That's fine. What you want to know, though, is in practice is you never know what u and theta are exactly. You only know them approximately. And you normally have some sense of how good you are. So in practice, you know the variability you have for it. And so knowing this, I now want to predict what the variability of my new measurement is. And why I want to understand what variability is at various points in time is when I do finally get a GPS reading from the satellite, I want to know how accurate my figure is. If it's super accurate, then I don't have to use the GPS very much. If it's all the way off, I really got to trust the GPS as much as I possibly can. But also knowing the relationship between all my 22 different states, the GPS will only help me work out the accuracy for my location, which is about 3 variables. So then if I know that all the connections, I can make predictions with everything else. That's the beauty of the whole system. So therefore, I need to really work out how the relationship between the change of v relates to the change of u's and thetas. It's non-linear, which is annoying. So a good simple mechanism, a really nice simplification, which works beautifully in this case, is to linearize a problem. And it really just boils down to just following the tangent plane. That's really what the heart of it is. So this is my equation. So a long-winded speech suggests that finding the tangent plane here is really helpful to work out how errors propagate and therefore getting a good sense of variability. So v is my main variable. So the tangent plane would be v minus its reference value is equal to the partial derivative of the main variable v respect to the first one u at our given point times by u minus u naught plus the partial derivative of v with my next vector variable, so theta, times by theta minus my reference point. And that's what I wanted to plug into. So what I need to know then is what u naught, d naught, etc. are. So let's just suppose that we have approximately, this is our best guess, u is 10, I think I'll write down. Yep, 10. And theta being pi and 6. So that's our current best estimates. We have to work out what v is, which we can do just by plugging in. So plug these numbers in. So you get 10 plus 0.1 times by cos pi and 6. That'll be 10 plus 0.1 times by cos of pi and 6 is root 3 and 2, which is 0.8, something like that. So approximately 10.08, I think it is. You guys perhaps work it more accurately than me. So this is a slight error term being introduced. So now we have all our reference values. These are really the reference points. Then we can plug in our general form of tangent plane. So v minus v naught is the partial derivative of this expression with respect to u, which we need to work out. So del v del u is equal to what, guys? What is this equal to? 1? Yep, excellent. And the other one we need to know is del v del theta in a second. Just waiting for people to answer. couple of various typing things in, which is good. So you're getting minus 0.1 sine theta. Thank you. So at first glance, I mean, I'll write them wrong thing first down. So del v del u would be 1 times by u minus its reference value of 10, plus the incorrect thing to do would be just to write down the minus 0.1 sine theta minus its reference value of pi and 6. So what have I done wrong? What's the mistake in how I've written it down? Anyone spot it? I guess not, that's fine. So the issue is that these two partial derivatives need to be numbers. So you actually need to sub in the value point. So when I've got minus 0.1 sine theta there, what I really need to do is I need to plug in the actual value of theta that we know in this case. So we need to plug in the reference value. And I would have to sub in the reference value for u too if I needed to. And so just simplifying it down, that's just u minus 10. Sine pi and 6 is a half, so that's minus 0.05 theta plus 0.05 pi and 6. And you can rearrange that, so v is equal to u minus 0.5 theta plus some constant that a calculator can tell me if I needed to. So that's how you work out the tangent plane in a given circumstance. So and I mentioned a few issues that you might kind of arise. So this is a tangent plane. If you had to work out a differential, for example, the differential just tells you what the pattern is in general. In that case, you do not sub numbers in. You'd leave these as the straight derivatives, which is what people get confused with at times. So as I said, this here, so the 1 here and the minus 0.05, so the two coefficients in particular, show you the relationship between the errors of u and theta and how the error of v is. And that allows you to give a sense of what the variability is for what v is, and therefore help them do lots of calculations. So this whole process, this idea of linearizing, is called, and this constant updating is called an extended Kalman filter, EKF for short. It really says the word from the bottom. So extended Kalman filter. Kalman's the name of one of the guys who worked it out. These other people did it too. And so as I said, it's used to update things on the fly. And the real key thing, the extended part, is the idea of using something like a tangent plane to approximate this non-linear object by linear stuff. And the heart really is used to partial derivatives. That's what it comes down to. The more complicated version uses lots more partial derivatives, but it does use partial derivatives to do this approximation. So just what really days, just covering a bit more partial derivatives sort of stuff. If you go and do the tutorials 1, 2, 3 now, perhaps with some of the advice that I've been trying to pass in these lectures, you should be able to do assignment 1 now, which is due soon, so 23rd of March, as I'm talking. In that assignment, just some other things is, there are marking criteria with it. Sometimes they don't tell you much at all, but it's worthwhile having a look at them because sometimes they do tell you exactly what I'm looking for, particularly when it comes to things like graphs. So please just read through them. It will help. It will just benefit you to make sure that you present your answer in the way I'm looking for it. Just want to finish up with some questions that people have asked. Now it's about 5 past. I only got these questions this morning when I came in. So these are sort of added on the bottom here. So stick around. If you need to leave, you need to leave. That's okay. So I've got a quadric surface here. I've already completed the square to make it easier. What I want to do is I want to sketch the surface Now I'll do it quickly. If you do traces for this particular thing, so if you're for fixed, Z and Y, both of them lead to hyperbolas. So if you did fixed, X gives you ellipses, and more precisely with a break in the middle, with a break. So when you've got hyperbolas in two different directions, it's a hyperboloid. When you've got ellipses in the other direction, with a big break in the middle of it, it means that the whole thing's split up into two pieces. So it's called a hyperboloid of two sheets. So that's a classification. So done super quickly. What I want to do, focus on, is how do you actually draw the thing? How do you actually draw the surface? Now I know it's uploaded to two sheets. How do I actually draw this thing? And that's what the question someone's asked. So what I would do now is I just go and find a picture of a hyperboloid two sheets. So they look like this. So that's what I'm doing. I'm just drawing it. That's what they look like. Now they all look like that, but I want to make sure the picture matches up to the stuff I've got at the top here. That's what it really comes down to. So a few things is I really would like to know the axes that this one's about. This is my sort of axes here. So you can see what I'm doing is I'm actually drawing the axes in after I've drawn the picture. So I need to work out what the picture thing is. So first thing is I need to know what the center is. What's the bang in the center here? That'd be really useful. And in this case, it's not the origin. I've completed a square, so it's really when each of the individual terms is equal to 0. Gives you the real card of it. So when x minus 2 is 0, so when x equals 2, when the y minus 1 plus 1 is 0, so when y is minus 1, when z minus 3 equals 0, when z equals 3, gives me the center. So I've actually drawn the axes not through the origin at all. I've drawn it through a point of my choosing. And the axes will be different as accordingly. So I've really put this, I've just drawn the axes through the center because it makes it so much easier to see and just label it accordingly. Then I just have to work out what these axes are over here. So the directions of that are fixed, so y and z give you hyperbolas. They will give you the bottom two axes here. So when you've got z and y being able to will give you the bottom two axes, and different values of x's will give you ellipses. So that would be the other axes up the top here. So this one at the top is really what corresponds to x. So the x-axis, this axis up here then, so if you want to give this as being the x-axis, well, it really isn't the normal x-axis anymore. It's when the x-axis really is when all the other variables are fixed. So this thing here is when all the other variables are fixed. So when z is fixed and y is fixed. And so that's an intersection of two planes which use a straight line, which is this thing parallel to the real proper x-axis. These other ones will be the same sort of thing, but related to the z and y-axis. So now they get, and again, how to work out which one's which is the fixed x's give the ellipses, so that would be what the thing at the top is. So that would be parallel to the x-axis. So this one over here would be z being fixed and x being fixed. And this one over here would be y being fixed and x being fixed. So this one is parallel to the z-axis. This one over here is parallel to the y-axis. So I've got my principal axis label. I've got my center label. The only thing that would be really helpful to identify it pretty uniquely would be to work out what these two vertices are. And then otherwise it's getting pretty hard to draw. So I've got to work out what the vertices are. And if you think about it, well, as I've drawn it, the vertices are going to be here when y is minus 1, when z equals 3. So y is minus 1, z equals 3. I can see that from the picture already. And so all I have to do is work out what the x value is, just plug it in. So you can do it 3 different ways. One, you probably would notice what the x value is anyhow when seeing where the break is. So when you're doing the traces, you'll probably notice there's a break in the break, and where it goes from ellipsis being defined, not being defined, that will give you the changeover point gives you the vertex. So you probably would notice it that way anyhow. But if you're doing it after the fact like I'm doing here, you're going to sub it in. So if I sub in y being 1, if I sub in z equals 3, I'm getting 0 squared. Y being minus 1 gives you 0 squared. So I'm getting minus x minus 2 squared equals minus 1. And what I'm trying to do is solve that for equal for x. So you multiply both sides by minus 1, square root, so you're getting x minus 2 equals the square root of 1, which is plus or minus 1. And so adding 2 to both sides, either getting x as being 2 plus 1 gives you 3, or 2 minus 1 gives you 1. So that would be the two vertices. So as you can see here, this axis here really is parallel to the x-axis as I've drawn it. So this is a way of drawing it. So just recapping what I've done here is I want to try to sketch some complicated quadric surface. That's what the goal is. I need to know what it is, so I've classified it by using the trace method. And in doing so, that will often pick up key points like vertices anyhow. And by completing the square, you can see what the center is as well. Then to draw the picture, I just draw the surface first without any labels at all, without even any axes. And then a personal way I find to do it is then I try to put in some labels after the fact. So I put in center, vertices is really critical. If I try to draw the standard axes, they're a bit all off the side, and it's really hard to understand and read it. So I find it easier to understand, at least for myself, is where the axes lined up with the shape I've got. But I just have to be careful how I label it. Now, if you read the marking scheme for this similar sort of question in your assignment, you have to label it sufficiently enough so that I can understand what it's coming from. There's not a unique way of doing it. It really is not a unique way. I'll accept lots of different ways of doing it. Certainly labeling key points like vertices and centers is really critical. And I think that's for your mass. But how you label axes is up to you a bit. I would expect you to be doing most of this on a computer, like the shape of it all. And Maple, if you're using Maple, will probably put in some axes on automatically for you. But they probably won't label that vertices in the center. But it'll give you some sort of framing, which would be helpful. But at least you've got some other bits. But adding a few more bits to whatever it's called probably be sufficient. But this is all doing it without a computer's help at all. So you're going to that was a question that someone asked earlier that I'm responding to. So again, as you probably worked out this first chapter, these quadric surfaces tend to be one of the harder aspects. So we keep coming back to it, which is fine. It's good to so don't be surprised if you find it a bit more difficult. Not everything's the same difficulty. And I'm just trying to look at it at different angles. Give me some time to soak it up. So again, you can fire other questions you want to. Last one. Let's do this quickly. Draw a contour map of x minus y squared and hence sketch the surface. So a contour map really is just saying I've got the function here and I'm going to set it equal to a constant k. And you can have different k's in mind, so 0, 1, 2, 3, whatever it might be, but let's make it general to give a sense for it all. I want to try to draw this. Well, now it's just a function of two variables, x and y, rather than three variables anymore. So it's just going to be a function. It's just going to be something in the plane. And you go, oh, that's just a parabola. I can see I got the one squared term, one non-squared term, so that's going to be a parabola. And trying to draw parabolas, I put all the squared terms on one side, so I've got y squared, and dump all the other sides in the one. So you get x minus k. It's sort of the standard way to write it down. If I want to try to draw it off to complete the square, which is not necessary in this case. So that's the sort of the standard format. What that looks like in general, a standard parabola has y equals x squared. This is the other way around. So being the other way around, um, you got, instead of going smaller face up, it's on the side, and where these individual terms is equal to 0 gives the vertex. So when y is 0 and when x equals k, so in general, this has a vertex of x equals k, y equals 0. And a few people leaving, that's fine. If you need to leave, let's go for it. And again, it's sort of a parabola on the side like that. So that's because of what x and y is being reversed, and that's what all the contours will look the same. All look the same, sort of things like that. What happens is the vertex is just shifting as you go through it. So let's just put a few things down. So this would be something like, say, k equals 1. If I did another one, k equals 0, just give what a few of them look like. How that was really badly drawn. So k equals -1 would look like this one, for example. So that's to give you an idea what some of the different contours are. And I'd have to draw it neater than that. I mean, if I was doing that for someone, I'd have to re-go it. But you get the idea. So in 3D then, if I try to do it in 3D, then each cross section is a parabola. And so this is, so at x, y. So that's one cross section is a parabola. The other one is over here. It's all different parabolas. So what happens, try my best to try to draw it, is you've got a slope going up here, and each cross section for these different parabolas. So it looks a bit like I can't draw it right. It's basically a big ridge. I might try to drive it in word, explain in words. So it's just a ridge. So this is the top. This is the edge of the ridge line, and it sort of folds away on either side of the ridge. So, and it's just most constant slope the whole way through. It's called, because every single cross section is exactly the same, it's called a cylinder. And because each of the cross sections is a parabola, it's called a parabolic cylinder, is the name of the surface, if you want a name for it. And that's my attempted try of trying to draw it. So there were two questions that other people asked, so I thought I'd just put them at the end there. Anything else? I mean, some people have stayed all the way in, so thank you for doing that. Any other questions you've got before I finish it up there? Yep. Do you have anything else, Michael? Yeah, partial derivatives. Okay. How would I finish the recording there?